Hi, I'm Scott Knockley. In this video, we're going to look at another inverse displacement solution for a spatial manipulator. So by the end of this video, you should be able to solve inverse displacement problems for spatial manipulators. In this example, we're going to look at the Rice 6-axis industrial manipulator. So unlike the previous example where we just looked at the main arm, in this case, we're going to look at the full 6 degree of freedom arm. So the 3 joints of the main arm plus the 3 joints of the wrist. So if you recall, we looked at this example of the Rice for the forward displacement. So you can go back to that video and you can see, where we got our D&H parameters from. These are the modified D&H parameters, and how we can take each row of that and find our homogeneous transforms for the Rice. We also showed that the forward displacement solution that defines the tool frame with respect to the base frame is just simply the multiplication of all those homogeneous transforms out. And we didn't do all of them, but we showed, we had T03 here and we had T36. And we're going to use these as part of our inverse displacement solution. Now, the inverse displacement problem is given the pose of the end effector or tool. So we'd be given the homogeneous transform describing the tool frame with respect to the base frame. What are theta 1 through theta 6? Now, our tool frame relative to the last link would be known, and it would be constant, right? Because you'd have a known tool on your manipulator. So we can take that knowledge into account, and we can actually then calculate T that describes 6 with respect to frame 0 as just simply multiplying our T tool with respect to the base frame times the inverse of tool with respect to frame 6, which is what we do here. So this can all be computed, all right, and this would be known, right? These are values, these are numbers, right? Because we were given T0 tool, we know T6 tool, so we can calculate T06 in terms of these values. So now our inverse displacement problem we defined as given T, the transform describing base, frame 6 with respect to the base frame. What are theta 1 to theta 6? Now, it's important to note that since the Rice manipulator has a spherical wrist, we can actually split the main arm solution from the wrist solution. So we can solve the position and orientation problems separately. So we're going to use the main arm joints to position our end effector, and then we'll use the wrist joints to achieve the orientation we want. Okay, so this makes our life a lot easier. So instead of trying to solve for 6 joints at once, we're only going to have to solve for 3 joints. So let's look at how we can do this. So we're first going to look at the main arm solution, which is the position problem. So in this case, we're given the position of our wrist center, all right? Remember, we calculated that here, so we know that. And we want to know what our theta 1, theta 2, and theta 3. Now, since the Rice has a spherical wrist, we know that the position of frame 6 is also the position of frame 5, which is also the position of frame 4. All right, so if we go to our forward displacement solution and find the transform describing frame 4 with respect to frame 0, all right, we can actually get that vector describing the position of frame 4, right, which is this piece here. All right, and you can see these are only in terms of theta 1, theta 2, and theta 3. So we can use that to solve for theta 1, theta 2, and theta 3. So we've just rewritten those here. So we know px, py, and pz, all right, and we're trying to find theta 1, theta 2, and theta 3. So we can first isolate theta 1 in these above equations by multiplying both sides by T01. All right, and so T01 is just T10 inverse, which is given here. So we take this matrix, we multiply both sides, and we end up with this set of equations here. All right, and so this is 3 equations in terms of 3 unknowns. Now right away, we can see that the second set of equations here, all right, and this corresponds to element 2, 4 of our homogeneous transform, it's just in terms of theta 1. So we can immediately use this to solve for theta 1. All right, so I just rewrote that here. So from element 2, 4, we have minus S1px plus C1py is equal to 0. Now, if you recall, in our previous video, we had a useful inverse displacement formulas. All right, and these are given here again just for your convenience. And you can see we have an equation of that form here. All right, so we actually would have 2 solutions for theta 1 in this case. So we're going to write down those 2 solutions. So let's jump back. All right, so using our useful inverse displacement formulas, we know that theta 1 can equal a tan 2 py px, or it can equal a tan 2 minus py px. And remember, an a tan 2 is a quadrant corrected arctangent function. So you should make a note, 2 solutions exist for theta 1. All right, we should also note that if px equals py equals 0, all right, our wrist will intersect z1. All right, so the wrist center will intersect the axis of joint 1. All right, in this case then, there's an order of infinity of possible solutions for theta 1. All right, and so you could choose theta 1 arbitrarily in that case. All right, so we've solved for theta 1. Now we're going to go and look at how we can solve for our other unknowns. All right, so one trick to try is just squaring and adding the 3 equations together and see what happens. All right, so let's do that. We're going to square and add elements 1, 4, 2, 4, and 3, 4. Okay, and if you do that, I wrote it out already because it's a bit of a mess. Okay, you get this. This is the left-hand side of the equation, and this is the right-hand side. Well, right away, you can see, though, some things cancel out. This term 2c1 s1 px py cancels with this minus 2c1 s1 px py. And then you'll notice we have a lot of cosine squareds plus sine squareds. Okay, so we can use our trig identities. So these 2 are going to simplify. S1 squared py squared, that's going to simplify. Similarly, down below or in the right-hand side, this guy is going to simplify with this one. And lastly, these are going to simplify as well. So taking all those simplifications into account, what we're left with is we have px squared plus py squared plus pz squared on the left-hand side, and those are all known, so that's good. All right, and then on the right-hand side, we have f squared plus g squared plus 2fg c2 s23 minus s2 c23. So it's a lot nicer already. When you see something like this, you can use our trig identities. All right, and so note that c2 s23 minus s2 c23 can simplify down to s3. So this term here is just s3. And that's great because now we have an equation simply in terms of s3. So we can write that out. So we have px squared plus py squared plus pz squared is equal to f squared plus g squared plus 2FG S3. Solve for S3. And we'll have px squared plus py squared plus pz squared minus f squared minus g squared all over 2fg. And then we know then that theta 3 is just going to be the arctan 2 of S3 plus or minus 1 minus S3 squared. All right, where we're just using the cosine squared plus sine squared equals 1 property to find C3. All right, you also notice because of the plus or minus, we have 2 solutions. All right, so 2 solutions exist for theta 3. All right, so we've solved for theta 1 and we solved for theta 3. Go back to our equations. Now we need to solve for C2 and S2, or in other words, to solve for theta 2. All right, so now we need to find theta 2. So we're going to use elements 1, 4, and 3, 4 to solve theta 2. Now if you look here, we have this S23 and C23 term. So we're going to have to use our trig identities to break apart S23 and C23. So we're going to call these equations 1 and 2. All right, and we can note that S23 is C2S3 plus S2C3. And we know that C23 is equal to C2C3 minus S2S3. So we can sub these into equations 1 and 2. And if you do that, you get C1px plus S1py is equal to C2f plus C2S3g plus S2C3g, and we get Pz is equal to S2f minus C2C3g plus S2S3g. All right, now keep in mind we know theta 1, right, and we know theta 3, and we're just trying to solve for theta 2. So if we rearrange those equations, we can get this. And these 2 equations are just 2 linear equations in terms of 2 unknowns, C2 and S2. All right, so we can write those out in matrix form, which I've done here. And now we can solve for C2 and S2 by taking the inverse of this matrix and multiplying both sides. So that's what I've done on this slide here. So we're solving for C2 and S2. So we just took the inverse of that matrix, which is given here, and multiply both sides. And if you multiply it out, you get C2 and S2 as such. With C2 and S2 known, we know then that theta 2 is equal to A tan 2 S2 C2, where S2 and C2 are defined above. Okay, so we've now solved the 3 main arm joints, and now we can turn our attention to the wrist, which will solve the orientation part of the problem. So this is now the wrist solution. So in this case, we're given the pose of our frame 6, all right? And we want to find what are theta 4, theta 5, and theta 6. Well, we know that the rotation matrix describing 6 with respect to 3 is just simply going to be the rotation matrix 3 with respect to 0 transpose times 6 with respect to 0, all right, which is here. Again, our subscript, superscript cancellation. All right, and we now know the values of this matrix, okay? So let me just undo those so you can see it better. All right, we know those. We just solved theta 1, theta 2, and theta 3. So this matrix is now known, and this matrix is known. All right, so the right-hand side is completely known. All right, we can go to our forward displacement solution to get the left-hand side. So these are the equations in terms of theta 4, theta 5, and theta 6. These are unknown. All right, but this whole side is known. All right, and so these would be known numerical values. So these are known. Okay, and for simplicity, we're going to we'd multiply that out, and we can just write it in terms of R11, R12, R13, R21, R22, R23, and R31, R32, and R33. And again, these are all known. All right, these are numbers that we know. So we know the right-hand side, and now we're going to use these equations to solve for theta 4, theta 5, and theta 6. All right, and now we have 9 equations, but remember, only 3 are linearly independent, but we have a bit more flexibility in terms of how we're going to solve for 4, 5, and 6. All right, so let's start with element 2, 3, all right, which is C5 is equal to minus R23. All right, so right away we know that theta 5 is just going to be the arctan 2 of plus or minus 1 minus C5 squared, C5, all right, where C5 is just minus R23, so we can actually just substitute that in just for completeness. It's going to be 1 minus R23 squared minus R23. Again, we use the cos squared plus sine squared equals 1 property to find S5 here. So we know that we have 2 solutions for theta 5. All right, so theta 5 is done. Now with theta 5 known, we can use elements 1, 3, and 3, 3, all right, to solve for theta 4. So we can rewrite these 2 equations, solving for C4 in the first one, which is going to be R13 over S5. And we're going to have S4 is equal to R33 over S5. Now, if S5 is not equal to 0, then our solution for theta 4 would be A tan 2 R33 over S5 and R13 over S5, right? Simply S4 and C4. All right, this equation is only valid if S5 is not equal to 0. All right, we'll come back in a few minutes to discuss what happens if S5 is equal to 0. All right, but let's first find the final joint, which is theta 6. All right, so we can use elements 2, 1 and 2, 2 to find our theta 6 term. All right, so here's element 2, 1 and here's element 2, 2. So we can solve for C6 in the first one. So we have C6 is equal to R21 over S5. And then we can solve for S6. It's going to be minus R22 over S5. And again, as long as S5 is not equal to 0, we can solve for theta 6. It's going to be A tan 2 minus R22 over S5, R21 over S5. All right, and so we've solved for theta 4, 5, and 6, but we have this case where, well, what happens is S5 is equal to 0, which is definitely possible. So let's look at that case. So if S5 is equal to 0, this means joint axes 4 and 6 are collinear. So if we were to draw those joints, so here is joint 4, this would be joint 5, and this would be joint 6. So when S5 is equal to 0, that means that joints 4 and 6 are collinear. So this would be Z4, and this would be Z6, and this would be Z5. All right, so we'd have these two axes collinear. All right, so that means the solutions to theta 4 and theta 6 aren't unique, i.e. there's an order of infinity of solutions exist, right? Because we can make theta 4 something and make theta 6 whatever it needs to be to get the orientation we want. So in this case, you could just choose theta 4 arbitrarily and solve for theta 6, or vice versa, right? You could choose theta 6 and solve for theta 4. We're going to choose theta 4, so it's going to be a specified value, and we're going to solve for theta 6 for this special case when S5 is equal to 0. Otherwise, we'd use the solutions we found for the other cases. All right, so from elements 3,1 and 3,2, we have these two equations here. All right. This is just simply two linear equations in terms of two unknowns, C6 and S6. All right. I didn't go through all the steps, but you can solve for C6 and S6, and you will get these two terms here. All right, and therefore, theta 6 is just simply the A tan 2 of S6 C6. All right. Where S6 and C6 are defined to the left. All right, so we would use this solution in the case where S5 is equal to 0. We'd specify theta 4, and we can use these equations to solve for theta 6. So it's just that special case. Now, you can see that we had multiple solutions for several of the joints. All right, and in fact, we had two solutions for theta 1. We had two solutions for theta 3. And we had two possible solutions for theta 5. All right, and what this means is for each theta 1, there's two possibilities for theta 3, all right? And for each of those theta 3, there's two possibilities for theta 5. So in terms to figure out how many possible solutions we have, you have to multiply this all out. And this means for some poses of our end effector, there could be up to 8 solutions to the inverse displacement problem for that serial layout. Okay? All right, and this is a figure showing that. Now this is a different layout. It's a similar layout to the rice, but it's a 6-axis robot. You can see the orientations are all the same of our tool in the position. All right, so they all have the same pose, but if you look, each configuration is different. All right, you have to sort of look at the features, but basically in this case theta 4 is here, this solution, and in this one theta 4 is this solution, and so on. All right, so this is an example of a position, or I should say a pose, where there's 8 possible solutions. All right, so you need to keep that in mind when you do your inverse displacement problems, this issue of multiple solutions.